exercise 2 from the worksheet 4. Here we have an equation as follows. It is the combustion of NH3 in gaseous state, and we are asked to calculate the standard enthalpy of formation of NH3. And then we'll calculate the standard enthalpy of formation but at different temperature. And the third question concerns the calculation of the bond energy in this molecule. So we first start by writing this equation. Now the standard enthalpy of reaction is given by the standard enthalpy of combustion, which is in this case delta H dC for combustion. It is the same as if we have written the standard enthalpy of reaction at a given T. And this standard enthalpy of reaction is equal to sigma standard enthalpy of formation of products minus sigma of the standard enthalpy of formation of reactants. And of course we have to take into account the stoichiometric coefficient. And now, because the standard enthalpy of formation of pure element is equal to 0, so here for nitrogen gas and O2, they are equal to 0. And also the value of the standard enthalpy of formation of NO and water are given. And the same thing for the standard enthalpy of this reaction or of this combustion. It is also given. The only unknown value is for the standard enthalpy of formation of NH3. So we can obtain the value of this standard enthalpy of formation from this equation. Now we'll plug the value of each enthalpy of these substances and of the chemical reaction. For NO we have 90.3 plus 3 times the standard enthalpy of water gas, negative 241.8. minus the standard enthalpy of combustion, negative 542.8. Now we do the math and we get a value of negative 46.2 kilojoules per mole. Now for the second question, we calculate the standard enthalpy of formation of this substance, but at different temperature. And here they say that the heat capacities depend on the temperature, and they are given. But in this case, we need first to write the the equation of the formation of NH3. An equation of formation is written using the elements in the standard state. To get the NH3, we have to start from nitrogen gas. It is the standard state of nitrogen plus hydrogen gas to give NH3 in gaseous state. This corresponds to the standard enthalpy of formation of NH3. And of course, we have to balance the equation. Here we have half for nitrogen, and here we have 3.5 for hydrogen. Now to calculate this standard enthalpy of formation but at different temperature, here we have the temperature of 298 Kelvin. So we need to apply the Kirchoff law, which says that the standard enthalpy of formation of NH3 at 373 K is equal to the standard enthalpy of formation at 298 Kelvin plus the integral between T1 and T2 delta Cp dt. Now we have, because this value is given, now we have to calculate the delta Cp. So the delta Cp is equal to the heat molar capacities of the products minus the molar heat capacity of the reactants. So here we have Cp of NH3 minus half Cp of H2 plus 3, or here we have for nitrogen, and 3.5 for hydrogen. Now we have to plug the value of each Cp. Now we see that the molar heat capacity is dependent on the temperature, and it has this form, A plus BT. So we can see this equation as A1, here A2, and here we have A3. And here we have also B1, B2, and B3. So we get an equation as this one. Plus the slope B1 plus B2 plus B3T. And the final expression of the delta Cp is as follows: negative 29.91 minus 9.5 times 10 to the minus 5 T. So here's the final expression of delta Cp. We have here A and B. So the integral of this equation between T1 and T2, A plus B T dt, is equal to A T plus 1.5 B T square between T1 and T2. Here it is. Now we'll integrate this and we'll obtain the final temperature or the final standard enthalpy of formation of NH3. So we return to this equation. So we have here the standard enthalpy of formation at 373 Kelvin, standard enthalpy of formation at 298 K, plus we have here the value of A times T at 373 minus T at 298 plus B, or 1/2 B, T 373 minus T 298, but both squared. And now we have to plug in the values. Here we have minus 46.2 kilojoules per mole plus minus 29.91 times 373 minus 298 plus 1/2 minus 9.5 times 10 to the power of minus 5 times 373 square minus 298 square. So here is, now we have just to check the unit before going ahead. So here we have this value in kilojoules per mole, and here we have the molar heat capacity, which is given in joule Kelvin minus 1 mole minus 1. Here it is given in Kelvin, so we'll get joule and mole. And the same thing here. So we'll have here, the Cp is equal to joule Kelvin minus 2 mole minus 1, because here it is the slope, that's why it is Kelvin minus 2, and here it is in Kelvin square. So we'll get here the unit for the second part of the slope is given in joule per mole, and here it is in kilojoule. So we must convert the joule to the kilojoule, and we have to multiply here this part. It must be multiplied or divided by 1000. So we have 1 joule is equal to 10 to the power of minus 3 kilojoules. So now we can cancel the joule, and we get at the end a unit in kilojoule per moles. And the value of the standard enthalpy of formation at 373 is equal to negative 48.45 kilojoules per mole. So we can notice that the variation is not that large. We have a change of about 2 kilojoules. Now let's do the last question. Here we'll have to calculate the bound energy of NH in this molecule. So we are given this bound energy of the triple bonds between nitrogens and of the bond between hydrogen. So we'll use the same equation, the reaction of formation of NH3. So we'll rewrite again the reaction. We have N2 in gaseous state plus H2 in gaseous state, which gives NH3, 1 mole of NH3 in gaseous state. Here we have the stoichiometric coefficient that we have to add. Now, to form a bond, we need first to break the molecules. So we need gaseous atoms that are isolated. So here we go through a second part. Here we have the delta H of formation that is obtained in the first question. That was calculated from the first question. Now we move through a different path. because enthalpy is a state function. So now we have to form nitrogen, isolated atoms, and hydrogen. So to move from nitrogen to nitrogen isolated atoms, we need to provide an energy that is equivalent to this bond. But here we have 1.5 molecule. And also because the bond energy of the nitrogen is negative, so we have to multiply by -1 in order to get an enthalpy that is positive. Breaking bond is an endothermic process, so it must be positive. And here the same thing, we have 3/2 the standard enthalpy of the bond formation between H and H. And here also we must multiply by negative in order to break the bond. Now to go from this to the final substance, we have to form here this molecule. Let's draw this Lewis structure. So we need to form 3 bonds. But here it must be negative because it is a formation process. When bond is formed, energy is released, which is an exothermic process. So now, because enthalpy is a state function, so we have the direct part and the indirect part. So we can write this. The equivalence between the standard enthalpy of formation is equal to the sum of -1.5 Now this enthalpy is known. The same thing, this bond energy is known and this bond energy is known. We have only delta H of the bond energy of NH that is not known. So we can obtain this bond energy. Now we plug the value in. And at the end, we get a value for this bond energy of -390.9 kilojoules per mole, which is about approximately -391 kilojoules per mole. So here is the bond energy NH in NH3 molecule.